Welcome, everyone. Let's just dive right into it. Today, in this explainer, we're looking at the ultimate practical guide to taking structural drawings and turning them into flawless site execution. And the best part? Doing it without wasting a single ounce of steel. We're talking about mastering the bar bending schedule, commonly known as the BBS, and we're going to focus specifically on concrete footings. So, before we hit the heavy math, let's quickly ground ourselves. A bar bending schedule, or BBS, is literally your blueprint translated into physical steel. It's a super detailed tabular record that tells you the exact size, shape, cutting length, and total quantity of rebar you need for a specific concrete element. Basically, think of it as your ultimate set of fabrication instructions. Here's our roadmap for today. We'll start with 1, the big picture, move into 2, decoding the design, hit 3, core mathematics, check out 4, the master output, and finally, wrap up with 5, site reality and quality control. Let's get moving. Section 1, the big picture, controlling the chaos. Look, creating this schedule is your #1 weapon for controlling costs and making sure the physical rebar actually matches the engineer's design. Without a BBS, you're honestly just guessing out there. A solid schedule gives you precise material calculations, flawless cutting, and perfect bending. And crucially, it gives you total wastage control and guarantees efficient execution on site. It literally takes the guesswork completely out of the equation. All right, moving right along to Section 2, decoding the design, from paper to steel. When you're pulling data off an approved structural drawing, there are 7 absolute must-haves you need before you even think about cutting steel. You've got to find the bar diameter, center-to-center spacing, number of bars, direction, the bar mark, concrete cover, and the shape code. Pay special attention to concrete cover and bar spacing, right? Because if you misread those, your entire execution is fundamentally flawed from the jump. To make this super clear, we're going to track one specific example throughout this explainer. Picture a 2,000 by 2,000 millimeter isolated concrete footing. It's 450 millimeters thick with a 50 millimeter clear cover. For the steel, our main reinforcement is 12 millimeter bars spaced at 150 mil center to center, and the distribution reinforcement uses 10 millimeter bars also at 150 mil. Keep those numbers in the back of your head. Okay, Section 3, core mathematics, calculating the cut. This right here is where a great site engineer really separates themselves from the pack. How do we figure out the exact number of steel bars for that 2,000 millimeter footing without just, eyeballing it? We need a foolproof formula to tell us exactly how many bars to drop in so we hit the structural design perfectly. And here is that exact sequence. Step 1, grab your available dimension, which is 2,000 millimeters. Step 2, subtract 2 times the clear cover to handle both sides. So that's 50 mil times 2. Step 3, divide that result by your center-to-center spacing of 150 millimeters. And finally, step 4, just add 1. Always, always remember to add that +1. You have to account for that very first starting bar in the sequence. So once you've got your count, you figure out the cutting length. This is the total length of the bar before you bend it. You're mathematically transforming a straight piece of steel into its final bent shape. Depending on the design, you have to account for L-bars, U-bars, hooks, and you have to make specific length deductions for every single bend based on the shape code. Why? Because steel actually stretches a bit when you bend it. Now, to translate that length into weight, you just need this one magic universal formula, d squared divided by 162. That simple equation gives you the unit weight of steel in kilograms per meter, where d is just the diameter of the bar in millimeters. Honestly, I'd highly recommend just memorizing these standard outputs. An 8 mil bar is 0.39 kilograms per meter. 10 mil is 0.62. Our 12 mil main reinforcement from the example, that's 0.89, and a 16 mil bar jumps up to 1.58. To get your total steel weight, you literally just take your total calculated cutting length and multiply it by these exact unit weights. It's that straightforward. Let's pull it all together in Section 4, the master output, building the BBS table. This schedule is your ultimate source of truth. It combines every formula we just talked about into one clean document for the fabrication yard. Looking at our sample footing, you see our M1 main bars and D1 distribution bars. We've got the 12 and 10 millimeter diameters, the 150 spacing, our calculated quantity of 14 bars each, the 2.6 meter cutting length, and boom, the total weights, 32.4 kilograms for the main and 22.5 kilograms for the distribution. It is perfectly organized. Which brings us to our final stop, Section 5, Site Reality and Quality Control. Okay, so we have our perfectly calculated schedule. Now we have to head back out to the physical site and actually execute it. Correct execution means following the drawings exactly, keeping those 50mm cover blocks in place and using precise bar marks. But if you drift from the plan, you're looking at dangerous mistakes, incorrect spacing, missing bars, and catastrophic steel wastage. Deviating from your BBS can literally cause a structural failure, whereas sticking to it guarantees safety and keeps your budget in check. To guarantee that safety, you absolutely have to run through a strict pre-pour final checklist. Verify those footing dimensions yourself. Check the bar diameters and count them. Measure the center-to-center spacing. Confirm the cutting lengths and bend shapes. Make sure the cover blocks are actually physically there. Validate the column starter alignment and check the binding wire. Literally, do not let those concrete trucks start pouring until every single item perfectly matches your BBS. When you do this right, your site workflow is completely seamless. Hour 1, you're reading drawings and counting. Hour 2, you're calculating lengths and writing the BBS. By hour 4, the machine is cutting and bending the steel. Come hour 6, you're fixing the rebar, maintaining cover, and checking alignment. And hour 8, final inspection and pouring concrete. It's a beautiful, perfect cycle from math on paper to physical fabrication. Our expert guide on this topic, Abubakar Bhavikatti, sums it up perfectly. He says, master the BBS and steel quantity, cutting, bending, and site execution all become absolutely effortless. This whole explainer is really about realizing that practical on-site knowledge is built entirely on this exact foundation of trust, quality, and precise math. So, here's the real question. Are you ready to take these exact BBS calculations, apply them to your next site pour, and just completely eliminate construction wastage? If you want to elevate your civil engineering game and build with absolute precision, the only thing left to ask is, when are you going to start drawing up your first schedule? Thanks for hanging out with me for this explainer, and I'll catch you next time as we keep decoding the world around us.